we're going to start talking about semiconductors. So everyone should, everyone knows that the most semiconductors, the most commonly used semiconductors, as I said, is in the element table, group 4. So let's just, okay, chapter 2. A very, very brief, we're going to move along fairly quickly in this section because we're just going to give you a sense as to how the semiconductor's characteristic affect semiconductor device characteristic and what are the key factors. So we're going to go through it I think we're going to wrap it up in week 2, if possible. But there's a lot to touch up on. But if you look at the periodic table, we know that most of the semiconductor, as I said, maybe 99% of semiconductors are belong to the group 4. So let's look at group 4. So start with what? The first one is carbon, right? Carbon, silicon, germanium. But in semiconductor devices, you're not only using the 4th group, that mainly as your substrate, you typically need dopants. As we already mentioned, there is extrinsic semiconductor, so you look for your neighbors. So the neighbors are group 3 and group 5. They can combine with each other and get something called a 3-5 semiconductor, but that's not the scope of this class. So mainly in this class, we simply use these neighbors as the dopants. So the neighbors are, someone want to help me? So we got group 5. On the left is what? No one knows? Periodic table. What is the one on the? 对着彭吕佳音给我知道。所以 what's this one? 好，我们要去彭，这是 boron. So we're going to just list 3. So that's the most commonly used. But actually, the one that will be a successful dopant is actually this one only. Or Indian at the end. Yeah, so I want to list it again. 彭吕佳音，对吗？音嘛 Indian. Okay. Okay, so let me highlight it. Okay, so on the right, what else? I go back to your chemistry. 国中什么？国中化学。Like on the right. What is? 啊？氮，对。Like let me write it down first. Okay, good. I'm going to use this. I want to circle it, and let me just draw it all, and then circle the ones that is being used in especially semiconductor. You can actually combine them, as I said, that everyone's talking about the next generation of semiconductor, which is gallium nitride. You can do gallium arsenide. You can do aluminum gallium arsenide. So it can pair up into a compound semiconductor. But in this class, we're not talking about compounds. We're simply talking about if it's a silicon-based or germanium-based semiconductor, what are the kind of element we use in this system. So let's just do the silicon-based thing. So you start with silicon. So what are the good neighbors, meaning that the ones that goes along well with silicon, which are boron, boron-acceptable, indium-acceptable dopants. So this will be my substrate. And these will be my dopants. So these are called the dopant impurities. We're going to talk about why they have to be friendly. Okay, so on the right side, I didn't even use my blue. There's more choices. There's phosphorus, arsenic, and antimony. These three are commonly used. So these are also dopants. So you will see these elements that are being played around in semiconductors. So before we actually talk about these elements being introduced into silicon, we're going to start discussing something. We start with the first one, which is, we'll go back to this list, intrinsic. So this will be let me use my notation. We're going to talk about intrinsic. Let's just talk about silicon. So intrinsic silicon, what is its atomic number? What is atomic number? How many? 14, correct. So its atomic number is 14, so it starts with 1s2, 2s, if I'm wrong, correct me, 2. So that takes up 4, and then 2p, 6, right? That take up 10. So what is being left is there's 4 valence, right? 1 is 2, correct. I'm sure I get it right. So that will be 3 what? You mean is it S2, P2, or what else? What's the other option? When it's actually inside a crystal, silicon substrates, I should say silicon crystals, are we call covalence bound. 共价键. So if you grow your, remember I show you the wafers. Those are silicon crystals, and then they slice it into wafers, right? So the silicon crystals are linked with covalence bound. So I have 4 more valence electrons. So there will be, we call 3. Let me do this, otherwise it will. 3sp. So there will be 2 electrons in the first orbital for 6 and 4. Right? That's 14. So how do you get your atomic number, meaning that the amount of electrons you have in silicon? So that's 10 in the inner shell. There's 4. So that means I have 4. We call the valence electrons. Let me be sure I write it. Okay? So this is an advanced question, and not necessarily advanced, but in chemistry, what does this mean? Yeah, what type of orbital? It's not S, or it's not P, it's called. 有一个名词，对不对？ Correct. It's called a hybrid. Hybrid orbital. So this particular hybrid orbital, if you want to visualize it, if you ever go into classes like solid-state devices, We'll talk about these hybrid orbital. How does the orbital look like? There's a, if you go to your physics class, it will be the s orbital is rounded and the p orbital is like in different, in each of the axes. But sp orbital is a hybrid orbital. It will look something, I typically refer them, probably cannot, I don't know what it, how do you say it in English? But I'm going to speak Chinese. 它像粽子，就是粽子有没有？粽子就是中间往外散开。So will look like 粽子英文叫什么？ I really don't know. Really? So we'll look something like this. It starts with the center, so we'll then have this and this. If I use it plain, it's very hard to tell. But you know that it's a 粽子, like, okay? So that it will be, each of the angle will be the same if you look at a, you know, perfectly wrapped 粽子, okay? So then it will be the sp orbital. So there's 4 sp orbitals. Okay? So then if I'm trying to, it's very hard to construct a structure in 3D. So I'm just simply going to use a 2D illustration. So what happened is that I would then have my silicon crystal look something like this. So each of the silicon crystal, remember, has 4 valence electrons. Therefore, there's 4 coming from the center and then coming from this side. So that the yellow one will be the ones that on the side. Okay, something like this. Just to illustrate that each of one of them will see. So if I'm the silicon in the middle, I will feel very content because I have A electrons. That is why this covalence bound is very stable, because it sees 8 and is sharing with the neighbors. So everyone, and also it's if you remember the key of covalence bound against, what is the difference between covalence bound and ionic bound? Does anyone know? Ionic bound is that it's a very unbalanced state because your electron, you wanted to donate your electrons. For example, if you're alkaline, you want to donate mostly. And if you're acid, you probably wanted to have the electron more. But this is covalence, meaning that it's a fairly balanced state because each one, the electron will be at the center. Everyone will contribute to the same force, to that electron. So it's relatively stable and it's covalent. Therefore, it will then construct a perfect crystal. If it's in perfect crystal, it will be something like this. So everyone is contained. It has a very strong bonding. That is why you have diamonds. There's also covalence bound. It's also the same, call it diamond structure. I should say it's called a diamond structure, not 粽子, but just to remind you. It's a crystal is in diamond structure. Okay? But if you flatten it out, it will look something like this. And what happened is that, because as I said, because these bounds are very relatively stable, therefore you will not have free electrons and holes laying around in this crystal. But because these bounds, even though it's stable, if it's subject to thermal agitation, we should say thermal excitation. So if I raise my temperature, let's say if I start my crystal at 0 K, then there's no energy flowing around in the system. Therefore, every one of these covalence bound are intact, meaning that they're perfectly linked. But if I give you some energy, what happens is that some of just the probability, there will be one that has a probability of collecting enough energy to break this bound. So if I have enough thermal energy to break the bound, what happened is that one of the electrons, so everyone is sitting in this classroom, everyone is contained. Someone just left. No, I'm just saying. So everyone is contained, everyone is standing, everyone is sitting perfectly. But if it's really hot, so people will feel agitated. So one of them stands up. Let's say if this room is packed, every seat is taken. So if one of the electrons stands up, what happens is that break the bound, and what happens is that you would then have some free electron. And then at the same time, where's my blue? You leave a seat. So you consider a silicon crystal as a packed room. Every seat is taken. So if one of the electrons stands up, it would then leave a hole. Okay? So what happened, once again, you have thermal energy which breaks the bound. And this energy is typically referred to as the band gap, Eg, which is the band gap. So band gap is the energy that requires to break the bound. For silicon, is about 1.12 eV. Or, well, let me use the top. Minimum energy to break I misspell it. A covalence bound. So as I said, in silicon is 1.12 eV. Does anyone know what eV means? 什么？能系 energy 对它 Eg 是能系，我说这是 eV the unit. This is in energy. Why? 电子叫什么？中文叫电子伏特，大家知道吗？ Okay, that's fine. So that's the energy required for one electrons to move 1 volt. Okay. Just so everyone follows. So once you have a thermal energy which is higher than energy band gap, we call the energy, this is called the band gap energy. So if it's higher, then what happens is that you then have electron hole pair. So the result is that one electron stands up, it will then create carriers, 1 electron, 1 holes. You have to make sure that you understand this because it's a charge neutral system. So you have 1 electron, which is a negatively charged. Let me write it more correctly. This will contain a negative charge and this will then contain a positive charge. And Q is 1.6 times 10 to the minus 18. Okay? Just so we're aligned. So each of this carrier, once one generated, it will be become a pair. It will always be a pair when it generates. It could leave in different directions, but these are become, so these electrons and holes then becomes, we call free. This will then become carriers. Once it's being generated as a free carriers, it can be moved by external forces, which we're going to talk about in the second part. Okay? Silicon. As we already know, it has a band gap energy. A problem. Of approximately 1.12 eV. What is the significance of band gap energy? It will actually related to the amount of carriers that can be generated, especially in intrinsic semiconductor, at especially we typically refer to as room temperature. So we're going to talk about this relation, band gap energy, EG. EG. So for semiconductor in general, we have all type of either semiconductor like silicon, germanium, or 3,5 compound semiconductor. Its EG ranges from, typically for use, probably 0.5 to 3 volt, 3 EV. 3 EV is gallium nitride for blue light. So this would also refer to the photoelectronic interaction between two, but that's out of the scope. But just to give you a sense as to the typical semiconductors being used are at the range, its energy band gap band gap energy range is 0.5 to close to 3 volt. And the other thing is that we're going to talk about electrons. There's free carriers. We're going to talk about free carriers generated by thermal, called thermal energy. Thermal energy is typically referred to as KT. As temperature rises, you have the Boltzmann constant, and then it will give you the thermal energy of the system. So once we have the free carriers, as we already said, if you consider, few of you have questions on that. I'm just going to talk about this a little bit more. So once one of the electron, so you start with a perfect crystal, and then once you raise the temperature a little bit, some electrons will then take up the energy and then break the bound. Did I? I misaligned. Let me align it back like this. Okay? Okay? Something like that. So let's say you start with a perfect intact crystal where all of the bounds are well bounded. And then what happened is that there's the thermal energy, and then this bound is being broken. And this electron, as I said, will leave the area and then create a hole. So if my electron leaves, you then have a free electron, and then there will be a hole. Left at the location where the electron left at the broken bound site. So how does we viewed for electrons? It's free because it's not bounded. It's not placed in a covalence bond. Therefore, it's free to leave. Meaning that if I apply an electric field in the right direction, this direction, electric field, what happens is that the electron will move to the where? Which way does it move? If I apply a field to to the right, the electron will move to the left, right? Because the electron carries negative charge. So this will be a minus Q. This will be a plus Q. So if I apply a field, what happens is that the electron will try to move opposite direction of the field, and the holes will move in this direction, the same as the electric field. So you would think that how does the seat move? It's empty seat. It's called a vacant seat. The holes is actually for hole. Let me write it here. It represents a vacant seat. Right? So let's say I'm going to use the analogy that we have a fully packed room. What happens is that if I'm starting to give out money in front, let's say there's a seat, and when the electron comes, not give out money, that should be. I start to give out money to the front roller. What happens is that the student next to the empty seat will want to come sit in the front. And the next to that will come sit to the front. And you will see that the empty seat will then move to the back. So that's why when I'm giving out money here at the front, you will see that the hole is essentially moving toward the back. Okay? So it's not really, so hole is represent a vacant seat, and the movement of hole is done by a group movement of electrons. So it'll be sort of like a sequential thing. So if there's an empty seat, so the electron on the right side. So there's an electron here wanted to fill the seat because the electric field will pull it over. So if there's a free electron, it will try to save the seat, so the hole will then move to the right. So it's like the seat moving around, 像大风吹这样. Okay, so so you have to understand it's not, the holes are not physically existing particles. It's just a movement of empty seats inside a crystal. Okay, good. Let me see what I want to talk. Okay, so then we want to see how many are they. How many of these free electrons exist in a silicon crystal in a certain environment? So the way to characterize this is we call it intrinsic carrier density. This is typically noted as Ni. And we know that because once these electrons are generated, simultaneously it will generate holes. Therefore, let me just define this. So we define electron density in the substrate in a crystal as N. So it's a unit of CM3. And then we're going to talk about hole densities. We're going to use P, which also is number of carriers per centimeter, per cube, per centimeter cube. Okay? So Ni will then, for intrinsic semiconductor, intrinsic carrier density for intrinsic semiconductor equals to N equals to P. They are all the same because one seat represents one student standing up. So it's all accounted for in intrinsic semiconductor. You want to make sure that this will be like the basic question in quizzes. So you make sure that your concepts are right. I'll ask you, in intrinsic semiconductor, what is the key characteristic is that its electron density is always equals to that of the hole density, okay? Because there's nothing eccentric. It's just intrinsically one electron stands up, it creates a hole. Okay? So as I said, what is the number? The typical number, I'm not sure I can remember the equation. Let me write it down first. So Ni, it's not a, okay, let me write it down. These are just constants. It's not very commonly used. So you will expect that the intrinsic carrier density would depend on temperature, of course, because it was excited by temperature. So it would depend on thermal energy. So there's a strong thermal dependency. And then you don't need to remember the equation. I just want to write it down as a reference for you to get a sense as to what are the factors that will affect intrinsic carrier density. Okay. So this number, what does it represent? So I'm just going to give you an example. Typically, we use room temperature. So we know that for silicon, Eg equals to 1.12 eV. We're just going to plug that into the equation. And we're going to look at what happened at different temperatures. So at 300 degree K, so that's about room temp. I don't know if people add these. So at 300 degree K, your Ni, this is the number to remember because we're going to use that quite a lot. This one. But for higher temperature, we know that it will actually rise exponentially because of this factor and exponential term. So if I'm rising the temperature to that significantly, like in a rocket, so that N will then equals to 10 to the 15. Just want to make sure I get the number right. 15. Yeah, 15. It will raise by 5 order of magnitude. Okay? So first of all, you will need to know that it's very sensitive to temperature. So this is actually not a very desirable feature because if I have a piece of material and if I'm operating this device at a very low temperature or height, like in the desert, if there's a 100 degree differences for most commercial product, you expect that it should be able to tolerate a temperature difference between about 100, so that you don't want it to have a drastic change in its characteristic because carrier density will then affect conductivity. We're going to talk about that a little bit. But then you don't want it its main characteristic, which is the carrier density, changes a lot. Therefore, intrinsic semiconductor is not very useful. We're going to talk about that. That's one of the things is that it changes a lot. The other thing is that for silicon, it is fairly low. So think about the density. So if you think about silicon atom density, so that means that how many atoms is there per centimeter cube? That's about 10 to the 20th, 22nd. Okay? So at room temperature, if your Ni equals to N equals to P, is about 1. Let's say just about 1 times 10 to the 10th. Sorry, this is cube as well. So if you differentiate the two, you do N over number of silicon. number of bonds or silicon, just number of atoms. That's about 10 to the 12. It's not 1 in a million, it's 1 in a billion. Meaning that it's very rare. Very rare. I always tell my students that you think about yourself as a miniature creature in a silicon crystal. You need to travel a long distance to meet a free carrier, to find an empty seat. This is a very, very rare event. It's less than the chance of winning lottery or this thing, just to give you a sense. So this is that's just one of the key important things you need to know. And the other thing is that it's very rarely, this is, we'll talk about this number or this equation. These are theoretical equations. You actually wouldn't be able to get really intrinsic semiconductor. As I said, I think I mentioned this briefly in our last class, is that the reason why the first device is made by germanium, the first transistors are made by germanium, the reason why is that it's more easily purified. If you can't purify, this means that I need to make sure that my silicon crystals are pure to this. That's, I don't know how many ppm, that's 10 to the minus 6 ppm, in order to see the quality of an intrinsic device. Otherwise, you won't see the intrinsic. Any contamination will actually dominate the behavior. So that is to say that if you go and buy the silicon wafers, you're probably the lowest, I should say, the lowest level you can get in terms of number of carriers will be maybe 10 to the 15th, 10 to the 14th is at the boundary, meaning that you cannot purify it enough to actually see intrinsic characteristic. This is mostly on textbook and exercise, but you don't actually see intrinsic silicon. You cannot actually get intrinsic silicon. That's what I'm trying to say. But just to give you a sense that the carrier density is very, very low, meaning that it has high resistivity. So I want to ask another question is that, what do you think of this intrinsic carrier density, this number to keep in mind for germanium? Do you think it's higher or lower? What do you think? You think Ni for G and Ni for silicon? I should say it will depend on at the same temperature. So that will based on what? So if temperature is the same, following the same equation, this is the radical equation. So it will depend on what? This, right? So which one is higher? Silicon will be higher? Intrinsic density? You think? No, you guess wrong, sorry. So this will be much higher. The intrinsic carrier density will be much higher. The reason is that Eg of germanium is approximately 0.6 eV. And this is much higher. It means that the way to think about this, to visualize it, is that if you talk about covalence bond, remember carbon, diamond is the toughest because it's closer to the atomic. It's not the, it's the second layer, right? Second layer electrons to create a covalence bond. For silicon, it's the third layer hybrid 3sp, right? Remember, it's the third layer. For germanium, it's the fourth layer. The further away from the atom is actually a weaker covalence bond. Therefore, it has a lower energy band gap. Therefore, it's easier to break the bond so that it's in a germanium world. Think about this. If you're in a germanium world, the chances of winning lottery is higher. Okay? Okay. So, as I said, for intrinsic, first of all, it's very hard. It's unobtainable. The second of all is that even though I could try to make it intrinsic, as I said, it's a very sensitive parameter. Parameter is very sensitive. So what typically is being done is that I wanted to introduce these carriers in a more engineering fashion, meaning that I wanted to put it as I like. As I said, you want to make sure that it's at a sweetness level as you like. So that's what we engineers like, is that everything in control. So how do you control it better or make it changing the number of carrier? How does one? So the question is that how to manipulate NP levels more freely. First of all, if you're doing with temperature, what happens is that this will be N equals to P. Even if you raise the temperature, it will still be N equals to P, because the number of seats is the same amount of the number of the people standing up. Remember that. So the only thing you can do is that you can change the temperature and make it more conductivity a little bit higher because they have more carriers. But you cannot freely manipulate the electrons and hole levels independently. So the next thing we wanted to do is then I wanted to do something called extrinsic semiconductor. Introduce to you the so what happened is that this is done by adding, we call it impurities. There's two types of impurity. One is the impurity that actually happens when you cannot, during the purification process, you cannot get rid of all the impurities. But then, what if I adding impurity intentionally? So this is deliberately adding, and then you want to find your friends. Okay, so we'll go back to the table. I forgot. I should have kept it. 4, 5, and 3. So you start with, I'm only going to use silicon. I'm just going to highlight the ones that typically commonly used. So phosphorus. Okay, so we're just going to use 3 elements. You look for your neighbors. And then we found, as I said, the reason with dopant is that you want to find the atom that actually works well with silicon. Meaning that even though if I look right on the right, phosphorus is fine. Left is aluminum. The problem with aluminum is that it's not a very stable atom in silicon. It does not bound with silicon very well, even though it's its neighbor. So first I want to start with talking about neighbors. Why do you want to, let's say, so I have my silicon crystals. We still have silicon crystals. So I'm starting with an intrinsic, this takes it, okay. We start with an intrinsic semiconductor crystal. And then what happened is that I'm gonna substitute this guy in the middle with it open. I'm gonna just take it, we call it substitution. It takes a few processes, but so I'm going to introduce let's say I'm just going to introduce a boron. First of all, you wanted to substitute in a perfect grid. You want to blend in and link with others. So remember, for boron, it only has 3 valence electrons. Therefore, once I put the boron in, there will be a hole. Okay? So a group 3, for group 3 impurity, it will create a seat, meaning that it will then accept, it will be allowed to accept electrons, therefore it's called acceptors. These are called, the borons are called acceptors. The boron atoms is acceptors because it can accept electrons. Okay? So because it only has 3 valence electrons, remember, I'm only having 3 hands. The others has 4 hands. I only have 3, so there's 1 left. 1 empty seat left. So it will then create, so acceptors, anytime I introduce it, so I should say acceptor, typically we'll give it a density. So the doping, we call it doping density. How many of these you put it into the system is called the doping density of acceptors, or I'll call Na. So there will be number of acceptors per centimeter square. Number of atoms per centimeter square. Okay, if I wanted to have numbers of boron. Not necessarily boron, but boron is the most common one. Okay, so when you pick the impurity, one of the key important things is that you need to make sure that the boron is in the crystal and it's being linked with other silicon. So that's called the activation of dopant, meaning that I cannot just come in and then stay on the side. If you stay on the side, it will be something called additional borons, not in the crystal. You want to make sure that you introduce these borons, and then the boron, the 3 hands, the 3 valence bound, actually bounded within the crystal. That's called the activation of dopant, to make sure that it's blended in. Therefore, you want to find something looks close. That's why you look for neighbors, because neighbors are close. They look mostly similar. You don't want to go, somewhere far off in your periodic table, find some exotic component, because that will not blend in as well. You want it to be blended in, to activate, meaning that it's bounded, and leave an empty seat. So it has to substitute with silicon and then mingle into the system. Okay? Just to make sure that you understand the point of bounding. Okay? So it will create, this will be so this type of material is called so key important phrases to take home are, these are acceptors. Group 3 impurities are acceptors, and its density is Na. And the other key important thing is that if I'm putting these in, because it creates more holes, it creates additional holes aside from its original holes, therefore is typically referred to as the p-type. If I do this, it's called a p-type semiconductor. When Na is introduced. Okay? So that's how you create a p-type semiconductor. So we're also going to do the counter type, which is the other type is the n-type. So let's think about how do you do n-type, making a deliberately introduce more electrons. So n-type semiconductor is that by doping, I want to introduce is 2 introduce additional electron, additional meaning that more than Ni, additional to plus something. We're going to talk about that. Which is additional to its background. You want to do it, introduce additional electrons to silicon, for example. So how do you do that? It's the same thing. And let me draw the crystal again. I start with a perfect crystal like this. Let me make sure that I draw it right. Okay? Start with that. And also, I'm going to introduce something on the right-hand side, which is the group 5. So we're adding group 5. By adding group, slow down. So typically what you do is that you add phosphorus. That's the most easy one. So you can add phosphorus or arsenic. Both of them work pretty well. So that's in semiconductor you will see phosphorus. You start with phosphorus, arsenic. Nowadays people goes to, we're going to talk about that a little bit, and antimony. These three are acceptable dopants for silicon. Okay, so let's just use phosphorus. So we're going to add a 5-valence electron atom into the system. So I'm going to add a, let me use the AS instead, because this would then doesn't confuse with P-type P. So I'm just going to add an arsenic. Remember, arsenic has 5 valence electrons. So 1, 2, 3, 4. And then there's an extra. Right, and then create an extra. So then what happens is that it will donate 1 extra electron to the system. If I introduce one donor, it will introduce 1 extra electron. Therefore, it's referred to as donor type impurity, or donor. So the doping density is density of donor are referred to as ND, and also in the units of number of atoms per cm3. Okay? Good. So the thing we wanted when we introduce these type of donors, the main idea is that we want to control the amount of electrons and hole densities in the system. So how does what happened when I put this in? So if I put a certain number of acceptors, for example, I put a certain number of boron into silicon, what is the final results in terms of carrier densities? Let me move to the right then. So basically we have two type of, let me just construct a table. So what you want to know is that we want to know that now we have 3 types of semiconductors to compare. There's the intrinsic, and there's N-type with ND doped, p-type with Na dope. Okay? So we want to look at its electron NP level. We want to know how that affects its NP level. Okay? So for intrinsic, you know what it is, right? For intrinsic, we know that the electron density and hole densities are the same. So this will be Ni. This will be Ni. Okay? And for N-type, what do you think? It starts with Ni, right? So it starts with Ni and donating a little bit more. So it starts with a level of 1.5 times 10 to the 10th and put it in maybe 10 to the 15 or 10 to the 16. So what do you expect would happen? It will then be something close to Nd plus Ni, right? And because most of the time, remember this is very, very low. This is, as I said, Ni is at the level of 10 to the 10th. Let me just give you a number, the typical or the lowest doping you can get. Typical Na and Nd range is probably 10 to the 15 to 10 to the 20th. These are typical doping ranges that can be done in silicon. Okay? So most cases, your doping level, rather Na and Nd, are mostly much, much larger than Ni. Both of them are, because you couldn't go down lower. As I said, it's very hard to purify to make sure that it's intrinsic enough. Therefore, you need to introduce dopants that's active and overrides the behavior. So this is typically referred to as Nd. Okay? About Nd. Let me use a different color. Let me rewrite it. So this will be Nd plus, I should say. Let me rewrite this. This will be Ni, which is very, very low, but I introduce large amount of donor, so then it would then close to Nd itself. Okay? And for p-type, what happened is that you start with also Ni, and then for holes, these are for hole density. These are electron densities. You can actually get that. Okay? So for hole densities, it will then be dominated by the acceptors being introduced. So I'm giving the acceptors, and then it will approximately be okay? So because my main control is on the type of N-type, meaning that I have the main control in electron density. So this will be much higher than the counterpart. We're going to talk about that. So this is typically referred to as we call this majority carrier. In an N-type semiconductor, this N electron is its majority carrier. In a P-type semiconductor, this is the majority carrier. So the counterpart was then, in an N-type semiconductor, what about its minority carrier density? So another notation you typically will see is, we call it N. So this is electron density. N stands for electron in N-type. So it will be approximately Nd. Another way to put this is like this. So this will then be P. This refers to the hole density P will be approximately Na. So if you see N is majority because it stands for electrons in N-type semiconductor. P stands for holes in P-type semiconductor. Okay? You need to get familiar with that because we have majority, therefore, what's the next? What are these? Minority, yes. There's a majority, there's of course minority. So let's look at minorities. So for minorities, this will be, as I said, if we follow the notation, it will be P in N-type. Pn will be minority. And in this case, this will be NP. So this will be electron in P-type semiconductor will become minority. So how does one find out the minority carrier density? What do you think? You think the minority carrier density will be higher? Minority is definitely less. But what do you think it will be higher than Ni or lower than Ni? What do you think? You think the minority carrier, let me ask you this. In the NP will be larger than Ni. This is a choice 1, this is choice 2. Which one? Pick 1 or 2. Only one can be true. Which one? So the way to think about this is that we go back to the room with seats, okay? So you start with some amount of empty seats which is available. So now if I'm introducing holes, meaning that I'm creating more seats. So let's think about this. For the N-type semiconductor, at the beginning you have certain amount of seats and certain amount of electrons. If you flood it with the system with more people, what do you expect the seats will become? I'm flooding this system with a lot of extra electrons because the donor coming in, giving out electrons. So there's a lot of electrons in the system. So if you see seats available, the natural seats, someone stands up, what do you think the probability of having an empty seats become? Become less. That's why you will see something like this. And it's much, much smaller. So how does one determine this? This will be determined by something called, we won't have time to go through that. It's called the mass action law. The reason why it's called the mass action is because it's the result of mass action of carriers. So it says something like this is that your N times P in a system is a constant. So this will become Ni squared. So Mp equals to Ni squared is actually the key. Let me write it down here. So your mass action law is simply N times P, number of electron density and hole density, the sum, the product of that will be constant at a fixed temperature, at a certain temperature, so at a certain temperature, it will be at a certain ratio. So it's like a seesaw. 像跷跷板, 就是 one up, the other goes down. The product of both will be the same. So because of this mass action law, this is the same as I said. If I have some empty seats, if I flood it with electrons, the probability of these seats existing will be down, will be lower. The same for holes is that if I starting with certain electrons, I'm introducing a lot of seats, then people standing up will be less. okay, because I can see seats everywhere. So the probability of a standing electron sitting back down, the chances will increase, therefore it will reduce the number of electrons. So then this will then, if we follow that law, this will then give us, let me use the same color. Because I already know the number of electrons, therefore I know this will be Ni squared divided by Nd. I should say, let me, Nn. And because this term is Nd, which is the given component, for electron as minority in p-type, it's the same. It will be, let me write it down. Mp equals to Ni squared in pp. And this will be Na. Okay? So this will actually tell us that if I'm putting in impurities, dopants or receptors into the system, I could actually determine its electrons and hole carrier density. Definitely. I can actually control it very well because it will depend on doping concentration. For minority carrier, of course, it will depend on the inverse of that. But it will be a given number. You can actually very well predict its level easily. Okay? This is good? So before I let you go, we're going to go through an example just to see how much control is there in terms of levels of carrier density. So if you go buy a piece of silicon, typically they will give you resistivity. You can get resistivity. We're going to talk about that a little bit. But let's say I've given you a p-type. Let's say you bought a silicon wafer, the wafer that I show you, with doping level, which is Na. It's doped with a receptor type of dopant, which is mostly boron, 10 to the 17th. So this is the doping concentration you can actually introduce into the system. So we already know I asked you to find majority and minority carrier concentration. So there's two concentration. One is its majority. What is its majority carrier? P, yes, it's holes. So its majority carrier is holes, so we're looking for PP. This is the majority. So what is it? 按到前面, yes. This is Na, 10 to the 17th. Okay? And then, just to remind you that if you look at the doping concentration, it has to be much, much lower than silicon atom density because you want to make sure that it's still silicon. Silicon is the main construct of the crystal. So that is why if you dope it into very high level, if you put more than 10 to the 20th, you will reach something called solid solubility. It's like putting sugar in water. There's a limit as to how much you can put in. So then 10 to the 20 is probably the limit. But silicon is still the main construct of the material. So typically you will have something 10 to the 20th is on the higher end. and 17th is pretty much in the middle. So let's look at, this is the majority carrier. So let's look at the minority. Minority is electrons in a p-type semiconductor. Electrons are minorities. So this P stands for in p-type. Let me emphasize this is in p-type. So the subscript is just to label the type of material we're discussing. So because it's inverse, so that's minority. So it equals to Ni squared divided by 10 to the 17th. So this will be somewhat, this is 2.2 times 10 to the 20th, about that, 10 to the 17th. So you get a number of 2.2. Okay? So if you dope, even with a little bit, it's not very heavily doped in this case, you will see the contrast between the two type of carriers are very, very drastically different. Even though I'm not doping to a very heavy level, this is very low. This is the same. As I said, you flush it with a lot of seats, therefore no one's standing. Okay, so this is p-type. Okay, good. So I think we're just gonna end it here, and then think about if you have any questions, or if you have questions, you're welcome to email me, or I think the E class also allow us to communicate through, you can ask questions online as well. So if you want to use that system, that's fine. Okay, good. So let's end it here. I want to remind you all not to give stress. We have our, if you go back to check the syllabus, we actually have our first quiz in 2 weeks. So just make sure that you're aligned with the progress, otherwise you're shocked with the quiz.